2, 1, and here we go. Bond length. We had just barely gotten to this slide. Baby pointed out that I accidentally put a wrong letter, and then we were talking. We good? Did we talk about it at all or just laugh? Okay. The size of the atom's core makes a difference, and the bond order. So let's make sure we know what we mean by both of those things. All right. So bond length means the distance between the two atoms. Like, is it that long, or is it that long, or is it that long? Like, that's just what we're measuring. And you may remember we found it on these weird graphs that it was like right there. That low point was the most stable, and this measurement from here to here was the bond length. Okay, so the smaller the nuclei, the shorter the bond length. So fluorine's going to bond with something, it's going to have pretty short bonds because it's really small. Fair enough? All right. The size is not the only factor. Bond order is important as well. Bond order sounds more complicated than it is. It just means, is it a single bond, a double bond, or a triple bond? So here's this. It's kind of hard. I might make it bigger, I guess. Here we go. So in a single bond, that means one pair of electrons are shared, or 2 electrons total. It's the weakest of the 3 of them. It doesn't mean it's a weak bond, but if you're comparing a single to a double to a triple, it's the weakest. So we have the bond length then would be the longest. More distance between the nuclei. Then you have your double bond, and that would be the like middle strength, middle length. And then a triple bond is the strongest and shortest. So we breathe oxygen, and oxygen is like this. It has an O and an O and a double bond. But 78%, 77 point something percent of what we breathe is nitrogen. What does our body do with nitrogen? Nothing. It goes in. The air is 72 point something percent nitrogen. It's only 20 something percent oxygen. So every breath we take in, 3/4 of it goes into our lungs and does nothing. It doesn't react. It doesn't do anything. Any ideas why? Okay, we don't have the ability to break that triple bond inside our lungs and get any of the energy out of it. So, but our blood is pretty dang good at processing oxygen. Okay, then, hold on. If I had fluorines or chlorines, then it'd be too good and I'd breathe it in and it would kill me. Okay, go ahead.
Never mind.
Okay, fair enough. Okay, so look your partner in the eye and tell them the 2 things that affect bond length and how they do it. Your partner's ignoring you, so let's do. Okay, size and order. The smaller the atom, the shorter the bond. So those are directly. All right, and then bond order. Single shortest, or sorry, I screwed that up. Single longest, triple shortest bond length. Okay, with that, we're going to have a summary question here in a second. All right, there's more. Oh, yeah, it's right here. All right, this is just from one of the AP videos, if anyone's watched them yet. The potential energy diagram is given for C triple bonded to O. carbon monoxide. A student claims that the curve for a C to O, a single bond, would be less deep and to and we shifted to the right. I didn't type that. That's from an AP. They don't ever screw up. It's weird. That makes me happy. They didn't like put any drug paraphernalia in it, but that's okay. Be less deep and shifted to the right of the curve for C triple bond O. Do you agree with this claim? Explain why or why not. Okay, so the student says it would look like this. That's not shifted enough. Something like that. You okay with that? That's what their claim is. It's less deep and it's also over here. Do you agree or disagree? Speak with your partners. How's your conversation going? Good. How's your conversation going? Good. How's your conversation going? Good. How's your conversation going? Okay. All right. So here we go. First off, do you agree with the student? Yes, you should. You should agree with the student. They are correct. It is a longer bond length that accounts for the shift to the right. And it is because it's a single bond, right? Okay. And then it's less exothermic because once again, it's a single bond. There's less of an attraction, so it would take less energy to pull it apart. That was not suspect at all right there. That's completely normal behavior. Okay. This is on the AP test, questions just like this. All right. Not bad form. Okay, here we go. Lattice energy. Sorry, I can't not judge people's running and their walking. I don't know. I don't judge them. I'm not like, oh man, he's trash. But I'm like, oh man, they can't walk very well. Can you walk really well? I walk okay. There's just very distinct things that people do. I'm medium. You just want me to get distracted. I will just tell you, you should walk one way and not the other. Which way is the right way? The way I do it. There's about 10% of the population that locks their legs straight before they hit the ground. And that should never happen. Then there's about 1% that has hyperextended knees. Anyway, that's really bad for you in the long term. If you don't know what I'm talking about, just watch. And some people you'll see that like they're straight and then they hit. And then there's a lot of people where they plant and their knees like vibrate. Watch Jesse Roberts walk from behind someday. And you'll see what I mean by like the side to side. You're like, man, Roberts, you have no stability. You're like, I know, I went and got an MRI and I don't have anything. So, but it's more pronounced in girls, the bad walk. So moving on. Here we go. Coulomb's law. Are you serious? Yeah, I am. All this stuff. Oh, it's cut off. But all this stuff is like been talking about forces in chemistry and how that affects molecules and their structure. Well, the only force we're talking about is Coulomb's law. So it's over and over. Coulomb's law can be used to understand the strength of interactions between cations and anions. So most of what we've been talking about, like on the previous slide, was covalent. This is talking about ionic bonds and their structures. Their structures, the energetics of it is called lattice energy, which we saw yesterday when I lit the magnesium on fire. You saw evidence of this lattice energy. Okay, if you don't understand anything I say, at least know that the highlighted part of this is what you need to 100% know. And that's because interaction strength is proportional to the charge. All right, that sentence right there is saying that it's Q1 times Q2. It means that the charge of one and the charge of the other, they're directly proportional to the force because they're on top of a fraction. All right, so the larger they are, the greater the force. That's just math. But then the smaller ions lead to a stronger interaction. Okay, the smaller is the radius or distance squared again. I know I've switched back and forth, but it's fine, it's the same. Okay, so large charges, big force. Small distance, big force, and vice versa. If you know the equation and you know that Q means charge and R or D means distance, you can just mathematically reason through these interactions.
Like do it like large charge, small possible ion.
So you want fluorine involved, and then you want like beryllium, really, but it's not really that good. So we would have to look at the tables to get it exact. Okay, now the next 5 or 6 slides, don't write anything, just kind of think about it. So we'll come back to this idea, but there are energetics of ionic bonding. Don't write any of this, please, because you don't need to. But it helps explain the lattice. So we learned last chapter, it takes 495 kilojoules per mole to remove electrons from sodium. This is its what? What is this called? It's ionization energy. To remove an electron, that's the ionization energy. So it takes 495 to remove sodium's electron. Okay, fair enough. All right, we learned from electron affinity that we get 349 back. Now, I'm not super good at math, but where's the thing? Here we go. 495 minus 349 is not a negative value, is it? No, which would mean it's an endothermic process, but it's not. It is not. So there's got to be something else, and that's this lattice thing. All right, so these numbers don't explain why the reaction of sodium metal and a chlorine gas to form sodium chloride is so exothermic. Now we could switch this. We could have said for magnesium and oxygen when I burned it, super bright white, right? All right, still the ionization energy and the electron affinity, it would have been endothermic, and it isn't. So there must be a third piece of the puzzle. What is yet to be accounted for is the electrostatic attraction between the newly formed sodium cation and the chloride anion. So it loses an electron and becomes positive. All right, so 11 plus is 10 minus, that's an overall positive. I'm pointing at the wrong one, aren't I? Whatever. So I just had them backwards. So sodium becomes positive, my chlorine becomes negative, and that attraction that they now have to each other causes them to go towards each other. That is movement. But when they come together, they don't move anymore. If they were moving and now they're not, that energy had to go somewhere, and that's given off as heat. So what we saw yesterday was the exchange of the electron, a positive and a negative being like, holy cow, let's hang out. And then they move and they bond, and that energy was given off as heat, and a lot of it, and white light. Okay, the third piece of the puzzle is called the lattice energy. Okay, you can start writing it if you want. This is the definition of lattice energy. Okay, I'm not even going to try. You get it. That's the energy required to completely separate a mole of solid ionic compound into its gaseous atoms. So it's essentially like the amount of time it takes you to like pull Velcro apart. Like that takes energy to pull Velcro apart, right? All right. Anyone know what lattice, anyone have a lattice fence? Anyone know what that is? You do? What does it look like? Oh, okay. Okay, thank you for being so committed. A lattice fence, it's a bunch of things that go this way, and then another board on top of it that goes this way. And they let like most of the light through, but like not all of it. So it's kind of private, but it's kind of not. You know what I'm talking about? They're wood. All right, they're called lattice when we overlay things on each other. Okay. When we have a lattice energy, I'll show you the picture. I'll come back here in a second. Where is the picture? Holy cow. We have a very organized structure. And the lattice energy is the energy required to pull that minus and that plus apart, and that minus and that plus apart, and that minus and that plus and that plus and all that. You know what I would do? I would put it in water and let it do it for me. And then I would use electrolysis and let it do it for me. Or heat it a lot. Okay, so here we go. That's kind of where it gets its name. The lattice means laid on top of each other and organized. Okay, the energy associated with electrostatic interactions is governed by Coulomb's law, my man. All right, we already said some things. We've talked about Coulomb's law for, I swear, a week or more. So once again, the electrostatic force, the attraction between the cation and anions is equal to K, which, what? I know, it's like K, that's not potassium. That's the electrostatic constant that I've been ignoring, and I'll still ignore it because it's always the same value. And if we're measuring how things change, then if this is a constant, I don't really care. You okay with that? So there is this constant. It is 9.11 times 10 to the 9th. It's a big number. All right. But we don't really care about that because we never calculate the force. We just look at how forces change based on changes. Okay, Q1, that'd be like the cation. Q2 would be the anion, or vice versa. It doesn't matter what order they go in, but it's the charge of your ions divided by the distance between them or their bond lengths. Okay, to have a big lattice energy, we need a small distance and large charges. Which, if I go back to this slide, what was highlighted? We need larger charges, makes a big lattice energy, and smaller ions, makes a large lattice energy. Okay. Lattice energy then increases with the charge in the ions. It also increases with decreasing size of ions. So here's just some examples. So lithium fluoride, there's your answer. Lithium fluoride has the highest lattice energy because, oh no, they're way over here, duh. Well, for plus ones and minus ones, lithium fluoride, then magnesium chloride, I guess, on this is pretty large, but then you get all the way to S, C, and N. Why would that be pretty large? Well, you have a +3 and a -3, all right? So you end up with a really, really large lattice energy. Now, you don't have to know these numbers, But you might be given a table that has these things, and it would say, account for lithium fluoride having the largest lattice energy. And how would you explain that? Because, well, it probably wouldn't have, it would just have these three. It would ask you, why does lithium fluoride have the highest lattice energy? Tell your partner for a minute. Of these three, lithium fluoride, chloride, and iodide, why would lithium fluoride have the highest? Keely? Okay. I'm going to move on in 10 seconds. You okay today? I'm too boring, huh? It's me. Okay, so here's your answer. Fluorine or fluoride is smaller than chloride and iodide. Meaning, if we want to throw in Coulomb's law, meaning that the distance is smaller, which makes the force larger. That's all you got to say. And that was a lot, I guess. Okay, the other question would say, like lithium fluoride and magnesium chloride. And it would say, account for the lattice energy of magnesium chloride being roughly twice as much as lithium fluoride. Okay, is it size this time that we've really worried about? No, we've just doubled the charge, right? Okay, that we're talking about the numerator. When we have these, we're talking about the denominator. Okay, so I have some questions for you. The energy required to separate the ions in magnesium hydroxide crystal lattice into individual Mg+2 and OH-, as represented in the table below, is known as the lattice energy. As shown in the table, the lattice energy of strontium hydroxide is less than the lattice energy of magnesium hydroxide. Explain why in terms of periodic properties and Coulomb's law. Are we changing the charges? Nope. So it must be the other. So tell your partners, what do you think? Yes, Gabe. Of what? I have no idea. We're too complex. And most of what we're made out of is covalent bonds. And we don't calculate lattice energy for those. All right, ready? We're not changing charges, so we must be changing size. So you would say something about magnesium being smaller than strontium. Is that a good enough answer? No, it needs Coulomb's law, right? So you need to explain that the smaller atom would make the distance between them smaller, which would make the force of attraction greater due to Coulomb's law. That's all you have to say. I would use the word Coulomb's law. How do I know what?
I don't know if we're looking for any size.
It didn't say anything about the size. It's showing you the energy changes, but we have to account for them. And based on that, we know we're looking for size because these are the same charge, +2, +2. So in Q1, Q2 over R, these stay the same. So it must be size I care about. Okay, here we go. Of the following pairs, answer these with your partner. Of the following pairs, which would you expect to have the highest lattice energy when they form an ionic bond? You don't need to explain your reasoning. Let's just take a second here. Mackel, Lickel, Rubugel. You can read it. They're all in family 1. and they're all with chlorine. What? Yes.
Oh, yeah.
All right, based on everything we've said so far, are we ready? Is this one testing us about our knowledge of size or charge? Size, because all the charges are the same in each example, right? We have +1, -1, +1, -1, +1, -1. So the numerator stays the same the whole time, right? So it must be investigating the denominator of Coulomb's law, which is the size. So which one has the highest lattice energy? Lithium chloride, because lithium's the smallest atom. Now, this one down here must be testing our knowledge on the charge. So the top, this would be a -1. The bottom, a -2. I don't know, I said bottom. The middle one, -2, and this one's a -3. So we would expect aluminum chloride to have the highest lattice energy due to aluminum being a 3 and the other ones being less, making the force greater. All right. All right, don't write anything. This phenomena also explains the octet rule. Metals, for instance, tend to stop losing electrons once they attain a noble gas configuration because energy would be too expended that cannot be overcome by lattice energies. So our lattice energy for Na and whatever, let's say it was Cl, wasn't it around 1,000? So if it takes 4,500 and my lattice energy is only 1,000, then I have to put in 3,500 more. That's just not reasonable. I could get it to happen, but I have to put the energy in. It's not going to happen on its own. So once things become an octet, that huge ionization energy is too large for the other parts of the energetics to overcome. Okay, boom. That one was okay. This one's super simple, and it's almost always tested like, where are you? Like this. Okay, this one won't be hard. We want to, this is the thing I was looking for earlier. The overall thing we've been doing for the last 3 days is atoms or ions bond due to interactions. That's the forces between them forming molecules. Okay, represent, that means draw or look at a picture. An ionic solid with a particle or particulate model that is consistent with Coulomb's law and the properties of the constituent ions. Okay, you have to draw once in a while. It will say like, draw a diagram of magnesium chloride. All right, here is the wrong way to do it. The magnesiums don't want to be next to each other. Now I could put a Cl here, a Cl here, a Cl here, an Mg, a Mg, a Cl here, an Mg, and a Cl here. I must have the negatives between the positives. That is literally all that matters. Okay, if you were not putting Mgs, you would have a +2. Well, I don't know why I wrote that so small. And a -1, a -1, a +2, a -1, a -1. That is really all it's saying. So here we go. The cations and anions in an ionic crystal are arranged in a systematic periodic 3D array that maximizes the attractive forces among cations and anions. That means you put them next to each other, and minimizes the repulsive forces. which means you try your best to keep them away from each other. That is it. So the test questions look like this. A student incorrectly draws the following particulate model of lithium bromide. Explain the student's errors. There are 2 of them in the particulate drawing. I don't know why that's hard for me to say. Sure. What's one of them? All right. That is definitely wrong. Look where lithium is. Now, I know it's left. I'm aware that, well, left is bigger than right. But lithium has 3 total electrons, 3 protons, right? How many does bromine have? 35. Like, it's huge. Even though it's on the right, it's huge. So Br, that's a plus sign, Tom. Br should be big and lithium should be small. Okay, and they wouldn't be in rows like this. So you would have, there you go, much like a checkerboard. Something like this, and it doesn't have to even be perfect. You should say Br and Li. You don't have to put that on all of them, but it should at least be more of a grid instead of just these lines, like a lattice. Okay with that? This one, it's going to be like 1% of the test or something like it. This should be an easy one. Don't put pluses and minuses right next to each other. Spread them out in an organized way to reduce their repulsive forces. Okay, below is a representation of a portion of a LiCl crystal. The student wants to draw the structure for KCl. Describe how the student should change this drawing to accurately represent KCl. Assume that they have similar structures. So you don't have to draw this. It just tells you, it's like, what would be different? There's only one thing that'll be different. They're not really farther apart. They are, but that's hard to say in your drawing. Seth, you look very nervous.
Would the CL, like what the CL is, would that be K in the way of the CL?
No. K is bigger than chlorine, which might be what you meant, Seth, but I would not write it that way. All you would say, this is how I would say, the black spheres would be bigger. And maybe say the black spheres that represent potassium would be larger. That's it. So, kind of okay? They're usually really short, really simple questions. They could be in the multiple choice. It could be like one of the points on a big, long, free response. It could be at the end and say, draw the structure of the lead 2 acetate before. Well, it wouldn't be that. It'd be like lead 2 chloride. Yes. We are, well, you're not done because you got to still study it and pass the test. I'm done talking about bonds for a little while. It's time to talk about Lewis diagrams. Thank you. Yes, these were made for you, or you were made for it. Here we go. All of these things are from AP because, I mean, they're way too cute for me to have designed them, for real. I mean, my slides have white background and black text. They're pretty fancy, but usually these are long. This one is that. Like, that's it. Lewis diagrams can be constructed according to an established set of principles. These, I hope you'll like them. And I hope, I never know, but they're not bad. Represent a molecule with a Lewis diagram. That's the whole goal. we'll spend the rest of today and some of tomorrow on it. Okay, Lewis symbols. Did we do electron dot configurations? Okay, I've drawn it. We didn't stress a ton on it. Like lithium, I put a dot that represented a valence electron.
So you just, you don't know valence electrons, so you don't draw
The core, yep, don't ever draw a core. So these will be slightly different because aluminum was 1, 2, 3 in electron dots. That seems familiar because the P's paired and then the 1. Okay, in Lewis diagrams, it's different. It's not an electron dot because these are when they're alone. Lewis is going to be when they're with something, and Al, it's not going to only bond with one thing. It's going to bond with 3 things. So like, don't stress about it. But I mean, they're similar but different. So here we go. The symbol for elements and their dots that represent valence electrons are Lewis symbols. Okay, we're going to talk about Lewis symbols and Lewis structures, which are almost the same. The Lewis symbol means for the element. The Lewis structure means when it's with something. Okay, so anything in family 1 has 1 valence electron. Are we okay with that? Which means we would give it 1 dot. It has 1 electron to give away. All right, family 2, it has 2. Now it puts those together. That's fine. They could be on either side. It doesn't matter. It has 2. That's what I care about. Family 3 has 3. Family 4 has 4. Family 5, 5, 6, 6, 7, 7, 8, 8. What? It's okay. The only exception here is helium only has 2 because that's all it wants, because it only has a 1s. Okay. Now, these are the representative elements. We ignore these. We're going to ignore them. Okay. So we have Lewis symbols. Next, we're going to have Lewis diagrams or Lewis structures. Okay, Lewis diagrams are models that represent chemical substances, show the connectivity between atoms, and display the bond order, single, double, triple, quadruple, between atoms, and they show valence electrons that are not used for bonding, which will be important for chapter 9. All right. So, like, I don't know. You seem like you're writing them down. You don't need to, but you can. But I'm going to go forward. So you might have to go to the film or take a picture of it. I'll give you 10 more seconds. Okay, actually, I'll give you a little longer because I got a text I should respond to from my boss. Okay. So here we are. A Lewis diagram for water looks like this. You will have an O, an H, and an H, and there will be a line or a dash between them. Then there will be dots represent or used to represent the valence electrons. So, I mean, it's already drawn, but you would, if you had H2O, you would put O in the middle because there's only one of it, and it's the more electronegative atom, and you'd put an H on each side. Then they're connected at least with 1 pair of electrons. Then you would complete the octet on any nonmetal. Hydrogen only needs 2, and it has 2. A line represents a shared pair. Oxygen then needs 2 more. 1, 2, 3, 4. 2 more pairs, I should have said. So this would be our Lewis diagram for water. If you look in a lot of books, it would look like this. And it looks like that because that's actually the real answer. And we'll learn why it's that way in chapter 9. But the main parts are the chemical symbols of the atoms, dashes to represent the bonds, and dots that represent the valence electrons. That's how we throw them together. Fair enough? Okay, so let's look at compounds formed between hydrogen and the nonmetals of period 2. So hydrogen and boron. Boron's kind of weird, but we would have an H, and then an H, and then an H. And then we would have a line. Now, is boron happy? No. What does it need? 2 more dots. Okay. So everywhere there was a single, we put hydrogen that had a single to share. Okay. Now this doesn't actually really exist, but it's good enough. Like it does, but it's not. All right, then C. This one's more simple. C has 1 dot on each side, right? Because it has 4 valence electrons. 1, 2, 3, 4, which means it needs how many H's to be happy? 4. An H with a dot, an H with a dot, an H with a dot, and an H with a dot, which would make C, H, and it would look like this because we represent electrons that are shared as dashes. I would accept either one, they're fine. Tell your partner how many H's N would need. 3. It has 3 that it wants to complete the its valence shell. Water, we already did, and we know it's not water. Well, it is water, but oxygen we know is H2O. All right, F needs 1. It's HF, and does any want any of them? No. These aren't super complicated. They get trickier. But so here's us walking through one. Just kind of go with me here. All right, so you'll be given something. And if it's not just easy like we just did, then you attack it here. Find the sum of valence electrons of all atoms in the polyatomic ion or the molecule. If it's an anion, add 1 electron for each negative charge. So if it was PO4 -3, we would add 3 electrons after we found the P's and the 4 O's. Okay, but we have PCl3. It's not a cation or an anion. So I know phosphorus is in family 5, so it has 5 valence electrons. I know chlorine's in family 7, so it has 7 valence electrons, but there's 3 of them. So this is 21, 5 plus 21 is 26 total electrons. Are we all right with that? I got sleepers. Right, that really means 26 dots. Fair enough? Okay, the next thing we do, we put the least electronegative element in the middle. So that's going to be phosphorus. It cannot be hydrogen though. How come hydrogen cannot ever be a central atom? It can only bond with one thing. Good job. Okay, so once we know, remember there was 26 dots, right? Then we put the structure together. We put the least in the middle and then surround it with the other atoms with a dash. And the dashes really were 1, 2, 3, 4, 5, 6. Okay, so we now are down to 20 dots. It's a lot of dots. Okay, next, fill the octets of the outer electrons or atoms. Why do we fill the outer ones first? They're nonmetals. Well, both of these are nonmetals. No. Because they are more electronegative. We just said in this slide, we put the least electronegative in the middle. So chlorine's going to fill up before it lets phosphorus fill up. So we complete the octet. And remember, we had 26 total. We had 6. You with me? That we used up. So we minus 6. And then we have 2, 4, 6, 8, 10, 12, 14, 16, 18. Right? So how many do we have left? 2. Any guesses where the last 2 go? On the central atom. Okay. Yep. It is not that bad. I mean, it gets a lot harder, but not a lot harder. It gets harder, but it's not that bad. No, not a billion, but like 50. Just kidding. We don't usually go past like 6 or 7. Okay. Now, let's look at here. So we have HCN. Let me just do it here. HCN. All right, that's cyanic acid. Let's follow the steps. This is in family 1, family 4, and family 5, right? So valence electrons, I have 1 plus 4 plus 5 equals 10. Okay, I'm going to put H on one side, C in the middle, and N on the right. H will always be on one side because it can only form one bond. C is in the middle because it's a less electronegative, which probably all of you said, I just didn't hear it all. And then there's N. Okay, connect them with a line. Now I had 10, correct? I have how many left? 6. It then says to complete the octet on the atoms. 1, 2, 3, 4, 5, 6. How many do I have left? None. Is carbon happy? No. So if you run out of electrons before the central atom has an octet, form multiple bonds until it does. So I come back here and I know carbon, it needs 8. It only has 4. So it needs a couple more. And then you have to, if you draw an extra line, you need to get rid of a pair. And I drew 2 pair, right? So those are gone. And now I have C triple bonded to N and then single bonded to H. So if you cannot complete the octet on the central atom, you have to make double bonds. Now, how come I didn't do this? H, double bond C, double bond N. Because you would look really dumb is the answer. H never forms a double bond because of what all of you just said. Okay. Let's just go here. We'll go to formal charge tomorrow. So just a couple of practice ones. Write these down and see if you can do them tonight. Like H2 should take you 10 seconds. You can probably do that already. Done. I'm about 10 minutes behind. I wonder how that happens.
We asked you at one.
Yeah. Really, it's because I like stuff too much. We already did this one. What? BR's in family 7. It would look like that. Okay, you guys are the best. Have a great weekend. Drive safe. Hopefully the parking lot's not a disaster.